In this video, we want to start the process of doing calculus on functions of several variables. And since both derivatives and integrals are based on the concept of limit, we need to first talk about what are limits here, just as we did in Calc 1. And this should look a lot like the definition we saw in Calc 1 here. So if I have a function of two variables, f of x, y, we define the limit as follows. We say L is the limit as xy approaches ab of the function f of xy, if for each epsilon bigger than 0 there exists delta such that if 0 is less than the length of xy minus ab is less than delta, then f of x minus L is less than epsilon. Right? In Calc 1, this was just an x minus a, absolute value. Well, the norm is essentially, the length of a vector is essentially an absolute value. It's the two-dimensional version of what absolute value does in one dimension. So anyway, if the distance between xy and ab is small, then you can guarantee that the distance between f of x and L is less than epsilon. If this is true for every epsilon, that you can find such a delta, that these x's give you close function values, then you have the limit. If you can't find such a delta, then you don't have the limit. Right? Now, the book we use gives this picture, and there's one thing about this picture that I'm not really crazy about. Right? So the way it works, the definition of limit works, says for every epsilon something has to happen. So you pick an epsilon, any epsilon. You're saying how close do you want your function values to be to L? This is what we think the limit is. We will accept in the range of L minus epsilon to L plus epsilon. And this is the part I don't really care for. They draw this like it's a little disk around L. It isn't, because you're just on the z-axis here. It's just L minus epsilon to L plus epsilon. It should be a line segment, right? So the thing is, once you've chosen for each epsilon, you pick an epsilon, you say, here's what I think it is. Can you find delta so that the x's that are, the xy's that are within delta of the point AB will give you function values that are within this range from L minus epsilon to L plus epsilon. If you can always find a little disk down here where all of these xy's give you the right function values, then you've got the limit. For every epsilon, you can find that little neighborhood, then you've got the limit. Okay, so just that should be a line segment, not a disk. This is a disk because you're describing a region in the plane of x's and y's. This is just a line segment. Now, theorem, and I'm just going to copy this out of the book too. If f of x and f of xy and g of xy are functions that are defined in a neighborhood of a, b, and L is the limit of f of x as xy goes to ab, and m is the limit of g of x as xy goes to ab, then the following are true. Okay. The first two don't have any. The first couple here don't have anything to do with f and g, but the limit of a constant is a constant. The limit of x is the x you're approaching. The limit of y is the y you're approaching. Okay. Now, this one says the limit of a sum of two functions is the sum of the limits. Remember, L was the limit of f and m was the limit of g. The limit of a difference of two functions is the difference of the limit. The limit of a constant times a function is the constant times the limit. This one and the first one up there make the limit a linear operator. Those of you who've had linear algebra, you might understand that. Those of you who haven't had linear algebra, well, you'll get it when you get there. It's not really pertinent to what we do. Product law, the limit of a product of two functions is the product of the limit, and the limit of the quotient of two functions is the quotient of the limits, provided you're not dividing by 0. And this is one of the places where we run into needing to do more work in order to figure out whether a limit exists or not, is when you end up with a 0 divided by 0, then it's like, well, the limit might exist. We need to do more work. If you had like 7 divided by 0, well, that's not going to exist. That's like an asymptote or something. But 0 divided by 0 means more work. But if L and M are neither of them 0, particularly if M is not 0, then this limit exists and it's the quotient of those two. This one is saying that you can take the limit of a function raised to a power and just raise the limit to the power. This is no different It's just that you're taking roots, which is raising to a fraction power. I don't know why they separate these two, but they say this for integers and they say this for roots. Whatever. You can raise the powers, you can take roots, and the limit just kind of passes right through that. They don't want necessarily to have negatives under square roots, but whatever. If that makes sense and you can do it, the limit works that way. Now, when the textbook gives examples of this, they go through and use every single rule. So, like, here's an example. I want to take the limit as xy goes to 1, 4. And they say, okay, so this is a limit of a quotient. So they take the limit of the top and the limit of the bottom. Well, in order to do the limit of the top, they say, well, this is a sum. So they take the limit of the x squared and the limit of the xy and the limit of the 3y cubed. And then they say, oh, but look, the limit of x squared is the limit of x squared. And we know the limit of x is going to be 1. Right? So you get a 1 squared out of that. And the xy, oh, that's a product. So this is the limit of x times the limit of y. Well, I know the x is going to be 1 and the y is going to be 4. And so it's 1 times 4. And they do step after step after step after step of breaking down all the things, using all these rules to essentially show that if nothing goes wrong, man, you can just plug in the numbers. Right? I just plug in the 1 for x and the 4 for y, and you get, the only thing that could go wrong in this case is I might be dividing by 0, but 1 plus 4 is not 0, so nothing goes wrong, and I end up with the limit is 69 over 5. Right? Now, it's not always that nice because sometimes, you're dividing by 0, or you're doing something else. If you think back to Calc 1, what ways did we have that limits could not exist? Right? And there was asymptotes was a problem. That is trying to divide by 0. There's right-hand and left-hand limits might be different, right? And so you have a limit from the left, you have a limit from the right, but they're not equal to each other, and so you don't have a limit as you approach that number. And then there was a problem of sufficient squiggliness, that if the function is just going up and down too fast as you approach, then there's no limit. I think we saw that when we were doing limits of vector functions, right? So anyway, here's an example of a limit that doesn't exist. The limit is xy goes to 0, 0 of 1 over x squared plus y squared. This limit would exist if I went to any other point besides besides 0, 0. If I went to 1, 4, then I would have 1 squared plus 4 squared on the bottom, and that would be the square root of, so that would be, 15? So the limit would be 1/15, right? But this does not have a limit as I go to 0 because there's a vertical asymptote there at 0, 0. The next example is kind of interesting. Definitely there's a problem at 0, 0 because the denominator would be 0. But there's also the numerator 0 at the same time. And as in Calc 1, 0 over 0 doesn't tell you anything. It means there might be a limit. It means there might not be a limit. Depends on what the functions are, and you've got to do more work. Okay? In Calc 1, we would factor and cancel, we would rationalize, we would do L'Hopital's rule, there's various things. In this class, well, we're not going to do much with limits. I don't really know of an equivalent L'Hopital's rule, so we just have to try different things. I want to show this example, though, as an example of one that has different limits as you come in from different directions. Okay? So what I'm going to do is I'm going to let y equals mx. So I'm going to approach 0, 0 by approaching along the line y equals mx for different m's, right, for different slopes. Now, by saying y equals mx, I'm going to replace my y's with mx. And notice, as x goes to 0 and you're on mx, the y is also going to 0. So what I'm doing is I'm taking this limit where it's got 2 variables in it, and I'm changing it into 1 variable because all my y's are being replaced by mx. And again, if x is going to 0, so is y, because I made this assignment that y is equal to m times x. So I am headed towards the origin here. But now I just had a Calc 1 problem, and I've got mx squared over, what is this, x squared plus m squared x squared when you multiply that out, right? But what happens here is I can factor an x out at top and bottom and cancel out, leaving the limit of m over 1 plus m squared. Well, the limit as x goes to 0. Not m, but x, right? And there's no x's in here. So this is a constant with respect to x. And so the limit is m over 1 plus f squared. Notice that this depends on m. When I come in along, say, the line y equals 0, right? So I come in along the x-axis. This would be a 0 over 1, and coming along the x-axis here, and I'm approaching 0. But if you come in along, say, the line y equals x with m equals 1, this is 1 over 1 plus 1, it's a half. As I come in along the line y equals x, I get up here at a half. If I came in along y equals minus x, then this would be at minus a half coming in this way. In fact, every single line you come in on, you get a different limit, right? Coming this way, it's there. Coming this way, it's up here, up here, up here. You keep getting different limits. And so the limit does not exist, right? Lots of different values as you come in from different directions. Now let's try another one. Here is x squared y over x to the fourth plus y squared, and the limit as xy goes to 0, 0. Again, this is a 0 on the bottom and a 0 on the top, so I need to do more work. I'm going to take a look at this just to let you see this surface. It's kind of a goofy surface. Something's going on there. It's definitely pinched. So let's analyze this. Let's try it in the same way we just did. So I'm going to let y equal mx, and replacing all my y's with mx, that looks like this. This is now an mx cubed on the top. There's an x to the fourth plus m squared x. I can factor an x squared out of everything and cancel that, leaving an mx on the top and an x squared m squared. Now this does depend on x, right? And so if I take the limit here as x goes to 0, well, the denominator is going to m squared, right? Because the m squared is not changing. This is headed to 0. So I have 0 plus m squared on the bottom, and I have a 0 times m on the top. And so that's a 0 on the top and an m squared on the bottom, which is 0. So coming in along any straight line towards the origin, it looks like I have a limit of 0. However, this is not the limit. If I come in on a parabola, y equals ax squared, here we go, let's do it like this. So my y's are now going to be replaced by ax squared, like that. And so now I've got ax to the fourth on the top. I've got an x to the fourth plus a squared x to the fourth. I can factor on x to the fourth and cancel it out. And now I don't have any x's in here. And the limit is a over 1 plus a squared, which depends on a. Depending on which parabola you come in on, you get a different limit. All of the lines looked good, but the parabolas look different. This is just crazy. So you might say, how do you know? How do you know that you've tried enough paths coming into the origin? One thing that I've seen done in some textbooks, ours doesn't do it, and I wouldn't expect you necessarily to be able to do it, is if you convert things to polar coordinates, this is only if you're headed towards 0, 0 does this work. You convert it to polar coordinates and you take the limit as r goes to 0. Because theta, you can be looking in any direction, but if the radius is getting close to 0, you're getting close to the origin. Right? So that's one way to do it, and it works reasonably well. It changes the problem into 2 variables to 1 because you're only taking r going to 0. You don't care what theta does. Anyway, I have one more example. Several years ago, a student challenged me saying, could you get one that's like coming in on spirals? You get different limits? The answer is yeah. I didn't type up in big to see what the function is here, but the function is f of xy equals the sine of the natural log of the square root of x squared plus y squared dividing by natural log of 1.2. So actually you can think of this as the natural log, so not natural log, but log base 1.2. And then minus the arctan. That minus arctan is inside of the sine. So I got log of the square root of this stuff minus arctan, and then take the sine of all of that. And it's kind of crazy, but this has this is the surface, and this is the contour plot. Why it's not plotting along the negative x-axis, I don't know, but bugging me. I'm trying to get rid of that, but I decided instead to make the video. So anyway, coming in along these spirals, it stays a constant height, and you get different values on different spirals. If you came in on a straight line, what would happen is it would look like the sufficient squiggliness. Is that this loops around infinitely many times as you go, as it zooms in. And so you would see up and down and 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 up and down infinitely many times, and there would be no limit coming in along any straight line. But there are limits as you come in along spirals. But the limit in total as you approach 0, 0 doesn't exist because you get different values in different directions. Anyway, there's the basics of limits of functions of two variables.